Hi everyone, I'm Paloma, an ML researcher working on large language models, dialogue chatbots, and reinforcement learning. In this talk, I'll be discussing this topic on continually improving LLM agents that converse and act. So, what is an example of a typical interaction of such an agent with a user? So, we have a user, think of coming into with a problem to an AI agent, for example, asking for a refund. The AI agent converses with the user to gather information, for example, their last name and their order ID. And then it acts by issuing commands to a set of tools, for example, making an API call to authenticate this user. The tool gives feedback as to whether the authentication was successful, and this interaction happens over multiple rounds until the agent successfully solves the task. So, how do we develop and deploy AI agents like this in practice for real world applications? So, based on my experience, I can categorize this as a two-stage process. So, if we were to plot the agent performance over time, it would look something like this. We have this initial stage, which we can call onboarding, where we want to launch the agent quickly with low effort. For example, a new application. We want to be able to teach new tasks to the agent quickly without using too much data here, but maybe leveraging higher human support at this stage. Once this agent is deployed, we start getting data, we move on to this stage of continual improvement, where we want to have an automatic data flywheel that takes in a continuous stream of data and improves the agent with very low human support. So let's define a framework for this kind of an improvement process. So we have an LLM agent here that is interacting with both the user and a tool that we will collectively call as the environment. The agent sends an action AT, and the environment gives back an observation OT, which is what the user said or what the tool returns. We might train such an agent with some initial corpus of supervised fine-tuning data. Now, most likely, this agent is going to make mistakes. So we need feedback to correct these mistakes. Now, this feedback can be either from a human or an AI, which is then added back to a feedback dataset used to continually improve the agent. In this talk, I'm going to focus on two aspects of this framework. One, we'll look at the question of LLM agent architectures and think about how do we easily scale these agents to solve complex tasks by leveraging modular architectures. In the second part of the talk, I'll talk about this question of learning from feedback. So how do we set up a process to collect feedback at scale to improve this agent over time? So let's begin with the first question on how we can scale an agent to tackle a large number of tasks. So here's the setup. We have an LLM agent, and we wanted to do a bunch of different tasks. We wanted to write code, we wanted to navigate the web, we wanted to automate complex workflows. To create such an agent, a popular approach is to prompt an LLM to generate a chain of thought reason and actions, also known as a React agent. So we first have like input instructions that describe the task along with some in-context examples on how to solve the task. We then provide a history of past observations and actions. The agent policy pi then takes in both the instructions and the history as inputs and predicts a reason and an action to take at a current time step. The reason here is the rationale or a plan behind what the action is. Now, you can see an obvious issue with this vanilla approach. The prompt, one being the prompt quickly becomes very large as the number of tasks and history of interactions keep increasing. Another is that if you keep adding new instructions for new tasks, it can cause regressions on earlier tasks since the model now needs to pay attention to a longer context window. So a natural solution to this problem is to fall back on a core software engineering tenet, that of modularity. So instead of one monolithic prompt, imagine we had a library of prompts. Now, each prompt or policy in this library solves a dedicated subtask. So you can think of a subtask as like a part of a task, like searching for orders or finding customers in a database. This kind of subtask prompts keeps each of the individual policy prompts small since it only contains the instructions and history for that specific subtask rather than the full task. Now, imagine if we had this library, how do we use this library? So given a new task, like issue a refund for an order, we would like to compose policies from this library. So you might first use the search order policy to find the order. And then depending on the order status, whether it's refundable or not, you choose what policy to call next. For example, either you issue a refund if it's refundable, or maybe you want to send a note to the customer if it's not refundable, as you can see on the left. Now, a key challenge to be able to do this dynamically is this kind of a decomposition of a task into subtasks isn't necessarily static, but changes based on the observation that you get at a time step. So the observation here being if it's refundable, you want to call policy issue refund. If it's not refundable, you want to call another policy send note. So how do we dynamically decompose these tasks into these policies or subtasks? So our key insight here is to enable any LLM policy in the library that you just saw to call any other policy in the library. What this results in is that you can have a dynamic chain of policy calls instead of having to predefine it statically. And you can track this dynamic change using a policy stack data structure. So this was the basis of some recent work that we presented at Column 2024, where we looked at this problem of dynamic decomposition of tasks to solve new tasks at test time. So to contextualize this step against existing planning and decomposition work, prior works like React or Synapse typically have a single prompt and optionally do in-context example retrieval for each task, which can be difficult to scale to many tasks because you would need some representative examples and instructions for each task. Other works get around this problem, like Adapt, Decomp, Ada Planner, where they also do different kinds of decomposition, but these are mostly static and don't take environment feedback when deciding the chain of policy calls. Step in comparison is both modular and is able to dynamically adapt to the environment feedback. So what does the algorithm look like? Let's say you have a task where the LLM agent needs to issue an apology to a customer unhappy with the product. Step decomposes this task by first calling a find review policy from the library, which gets pushed onto the stack, tracking the chain of policy calls. And that's what you see at the bottom. The stack is tracking that we made a web agent policy call, then CMS agent policy call, then find review policy call. Now, once the policy on the top of the stack, which is the active policy, finds the appropriate customer review by, in this case, clicking and typing in the browser, it gets popped out of the stack and handbacks control to the parent policy, the CMS agent policy, which then chooses to call another policy like search customer and pushes it on the stack, and the process continues. So you can distill this process down to one of three operations that can happen at any particular time step. So one, either the current policy calls a new policy that gets pushed onto the stack, or two, the current active policies interacts directly with the browser tool using clicks and types in this case, or three, the current policy terminates, pops out of the stack, and hands back control to the parent policy that called it. We evaluated STEP on a recent benchmark called WebArena. WebArena evaluates LLM agents on interactions with live websites and tools like Maps, GitLab, Reddit. And STEP was one of the top performing entries earlier in the year. So specifically, what we showed with this method was that you can get a significant improvement over prior works, increasing overall success rates from 15% to 33.5%, with most notable improvements on the Reddit and shopping environments. And STEP was able to cover a bulk of the 800 tasks using a library of only 14 policies. And of course, if you have more policies that have better coverage over the tasks, you can improve further with those tasks. But the caveat being that you need to add these kind of policies to the library. And interestingly, since we were using these kind of modular policies with STEP, it was twice as context efficient compared to a vanilla React agent that used a single prompt. So for a given task, you would typically require a lot less tokens being sent as LLM calls. And we also show some comparisons over prior works on other datasets like MiniWop++ that are covered in the paper. Yeah, so that's just a quick slide on that. But let me move on to just summarize what we looked at in terms of defining modular agent architectures. So we looked at this problem of running into intractably long prompts for agents that need to solve a range of complex tasks. And we presented a solution that leveraged a library of modular policies to dynamically decompose tasks at test time. Okay, now let's move on to the second question that we discussed earlier. Now that we have an agent set up, how do we go about collecting feedback from the errors that the agent is making so as to continuously improve the agent? So you have the agent now interacting with the user. As we saw earlier, the user wants a refund, and the agent attempts to call and issue refund action directly. However, it encounters an error. It forgot to authenticate the user before issuing the refund. How can the agent learn not to make this error the next time? Now, a natural solution here is to collect human feedback. So we can mark the incorrect action that the agent took, Y, as a rejected response, and send the context response pair, XY, to a human teacher. And the human rewrites and shows us the correct action, Y star. And this tuple of X, Y, Y star, sorry about that. So this tuple of X, Y, and Y star can then be used as preference data for training the model based on the correction that the human teacher provided. However, scaling such human feedback is challenging. You would typically need like a human in the loop to continuously evaluate the latest generations from the model. And also for these kind of agentic tasks, it is often difficult for the human to show correction in the same action space of the model. So the human would typically need to use the same set of tools that the model uses, which requires some training on the human side. Okay, so instead, we can, a natural solution here is to leverage feedback from an AI teacher. The AI teacher itself is an LLM that gets the context, the incorrect action Y, and generates a corrected action Y star. The obvious advantage of using such a teacher is that the student agent can now continuously query this teacher for new on-policy feedback as it is improving. The key limitation, however, is often when these tasks become very complex, the AI teacher itself might struggle to solve the task. So a key question then becomes like how to make the AI teacher stronger so that it can provide high quality corrective feedback to improve the student model. And our key insight here was to equip the AI teacher with something called a privileged state that is useful for solving the task, but maybe only available at training time. So if the AI teacher has access to this kind of information, they can distill it into a student agent so that it helps them solve the task at test time without relying on this privileged state. So what is the privileged state that I'm talking about? This can vary with different domains. So for instance, for a dialogue agent, this can be the conversation level sub goals that the agent needs to hit. For example, maybe on the training data, you collect some annotations and you have a ground truth set of API call annotations. And you know that a student agent has to hit those sub goals during the conversation. For a coding agent, this could be unit tests and solutions that a student agent needs to pass. And like for like things like web navigation or task planning, it could be the item locations, attributes, keywords that the student agent needs to hit. And these are things you can collect either from human annotations or from like simulator states, especially for things like task planning. So this was the basis of some recent work at iClear25, where we iteratively fine-tuned LLM agents on corrections generated from a privileged LLM teacher. And to contextualize this work, prior works in this area either don't deal with interactive environments where an agent acts and get feedbacks from external environments, for example, the Constitution AI, Direct OF works, or don't fine-tune models and instead self-refine at test time, for example, like reflection and related works there, or aren't able to continuously self-improve. Leap in comparison is able to fine-tune agent models that interact with external environments, and we can actually do self-improvement using privileged version of the model as a teacher, which we'll look at later. So let's walk through the algorithm step by step. Leap starts by training a student agent at any iteration I by taking the previous version of the student model by I minus 1 and making it interact with the environment and generating rollouts from this student agent model. Now, these rollouts, the ones that result in error, are given as trajectories to an LLM teacher as a context response pair XY. The teacher then uses the privileged secret state that it has access to provide the correction Y star. And then this tuple XY star gets added to a preference feedback dataset, which is then used to fine tune the student model for the next iteration and generate an updated model pi I, and this entire process repeats. So evaluate LEAP on a number of interactive decision-making benchmarks. The first is web shop, where an agent needs to find a product by searching for keywords, navigating pages, checking attributes, and backtracking when it makes a mistake. So here, Leap iteratively trains like a Llama 3 8 billion model using a GPT-4o teacher that has been equipped with a privileged state. And if you look at the table, the GPT-4o teacher, which has been prompted as a React agent, achieves a score of 58.4. Now, if you do just one round of training on the original SFT dataset, we get a Llama 3 8 billion performance with a score of 29.4. However, if you iteratively fine-tune and corrections from GPT-4o, we can drive up the score all the way to 61.8, where the much smaller student model at 8 billion can outperform a much stronger GPT-4o teacher model that has been prompted as a React agent. Over successive leap iterations, this is just breaking down the score metric into individual metrics. And you can see on some metrics, the improvements is greater than the other metrics. But overall, as you go from pi naught to pi 3, like the improvements are better. And the improvements need not be monotonic. It's just that one of the pi 1, pi 2, pi 3 should do better than whatever the original pi naught model was. Another benchmark that we evaluate on is this text game agent, where here we see pretty strong improvements, where the Llama 3 8 billion model is able to achieve a success rate of 91.8%, significantly outperforming stronger prompted model baselines like GPT-4o and Claude 3.5 Sonnet. And finally, we also evaluate on intercode in their Bash environment. This is an interactive coding environment. Now here the agent is tasked to solve a bash task by writing code, executing it on a shell, and getting terminal or execution feedback. Now coding is obviously a challenging task. So you can see here that the 8 billion model does have a significant gap from GPT-4o. However, if we train a larger 70 billion model in this iterative way, we are able to achieve a performance close to the teacher. Now, we talked about this privileged information and making this teacher powerful, but there is an important trade-off here where in how the teacher uses this privileged information and how realizable the corrections provided by the teacher are for the student. So what do we mean by that? So imagine on the one end, if the teacher used no privileged information, so it had pretty much the same information that the student had, the teacher performance itself is weak, but the corrections are easy for the student to follow because there is no information mismatch between the two. On the other end, now, if the teacher has access to full privilege information and the liberty to reveal it to the student at will, the performance of the teacher is strong, but the corrections are impossible for a student to follow. For example, the teacher just magically knows which link to click without giving a general rationale or a reason as to why the student should click on that link. So LEAP lies somewhere in the middle of this trade-off, where the teacher has been asked to use the privileged information, but not reveal it directly to the student. Instead, it can only reveal it as hints or general strategies for the model in its reasoning. And this is done by, the ablation here is done by changing the teacher's prompt to vary the amount of privileged information that they reveal. So you can see this effect empirically with that ablation, where the peak performance is achieved at the pi 3e point, which is a teacher which has been given the privileged information but asked not to reveal it directly, but only as general hints. And so pi 1e doesn't have access to the information, so the performance is low. But interestingly, giving all the liberty to the teacher to just reveal the secret information actually affects generalization of the student model pretty strongly and tanks the performance on the extreme right. Okay, And so finally, we also show that uh, that leap allows for self-correction. So in this experiment, instead of having a separate GPT-4o teacher, we use the same model, Llama 3 8 billion, as both the student and the teacher, with one key difference. As in the teacher mode, the model has access to privileged information, but in the student mode, it doesn't. And you can see that even in this setting, you can see a self-improvement by using the same model as the student and teacher. And here, I mean, the caveat would be that you do need strong privilege information. So if your privilege information isn't very rich or strong, then you don't like the student model. The teacher model is not more powerful than the student model to improve it. So something has to help it bootstrap and improve it. These are results on the AlphaFold data that you see these improvements. So you can see that from pi naught to pi 2, there is an improvement in the success rates. Okay, this was the second question where we wanted to look at how can we collect feedback at scale to improve the agent. And we looked at this problem of human feedback was hard to scale, but AI feedback is easy to scale. But the key challenge with AI feedback was that often it's complex for them to for a LLM to solve the task itself, and we got around this problem by leveraging privileged states to provide powerful corrective feedback that generalized to the student at test time. Okay, so looking ahead, there are several interesting problems towards continuously improving these agents for real-world applications, and I'll just touch upon a few of these. So one uh, definitely is around evaluation, where we talked about improving agents, but a very important question in obviously like when we're deploying these agents is that how do we evaluate whether our agents are actually getting better? So today we will typically evaluate these agents in a single step manner, where we pass in the context, the model output, and maybe optionally a reference output, and have an automatic LM evaluator that either scores on an absolute scale or provides like some pairwise um, win rates against a reference response. However, this kind of single step reasoning is often insufficient to evaluate and improve agents. For example, any agent response that deviates from the single step ground truth response is marked as a failure, even though this may eventually lead us to successfully solve the task in subsequent steps. So this is a very classic problem, even in RL and doing these kind of solving these multi-step problems. So in this problem, the idea would be that if you wanted to solve this in multi-step way, we need to be able to leverage simulators to be able to reason over these multiple steps. So for instance, we can roll out the agent with a user simulator over multiple time steps and see which actions led to success or not. And you can see, like, even though one of the branches deviate from the ground truth action at a particular step, it still resulted in a success. And being able to generate these kind of rollouts and seeing the consequences of different actions can unlock many interesting interactions. One, obviously, around like being able to evaluate these agents over multiple steps. Um, and there are interesting directions here on how we generate scenarios for these simulators so that they match the real world interaction statistics, or how do we adversarially test the agents by generating challenging scenarios to expose vulnerabilities. Beyond evaluations, we can also use this kind of multi-step rollouts to generate large-scale training data that allows the agent to self-improve, where it has these interactions with the simulator, generates positive, negative feedback data, and then that's something that we can train the model further on. And finally, we talked about evaluation training time, but you can also think of using these kind of techniques at inference time to efficiently search and choose actions that would lead to conversation goals being met. And I think there are lots of interesting ideas here, and it's like what's tractable given the inference time budget constraints that we typically have. Okay, so just summarize it here. So we talked about two key approaches for LLM agents that converse and act. We talked about step first, where we used a modular agent architecture for solving complex tasks. And then we talked about an algorithm leap that iteratively fine-tunes LLM agents to improve from privileged AI feedback. And we also briefly touched upon some interesting future directions in this area. Thank you so much for your time.